Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at the instantaneous rate of change of a function. In the previous video, I talked about slope of a curve, which is equivalent to slope of a tangent line to the curve. And in order to find either of those values, I had to use limits. If you haven't taken a look at that video yet, I would strongly advise you that you do so, because we're using that same concept today when we talk about instantaneous rate of change of a function. Before we talk about instantaneous change, I want to first talk about average rate of change of a function. So if we were given a function, y is a function of x, the average rate of change is basically the slope of the line joining the 2 points over the interval that we're going to look at. So if I wanted to know the average rate of change between this x value and this x value, I would find the corresponding points at those x values, and I would find the slope of the line that joins those 2 points. It's called a secant line. And to find the slope of any line with 2 points, we find the rise, which is the difference in the y values, or the dependent variable values, divided by the run, which is the difference of the x values or the independent variable values. So another way that I could state that is average rate of change of our function, so we could call it f of x or y. WRT means with respect to x, is defined as the slope of a line, delta y over delta x. And we've been doing that previously. We've talked about the slope of a line. However, the instantaneous rate of change of a function is often more valuable information when we're taking a look at the behavior of a function. So for example, if this represented the concentration of a drug in somebody's bloodstream, average rate of change just tells me over a certain time interval. Instantaneous rate of change tells me how it's changing at that particular moment in time. Similarly, if this represented depreciation of a vehicle, for example, I could find the rate of depreciation over an interval, or I could find it at a particular instant. So instantaneous rates of change are very useful pieces of information about functions. Since an instantaneous rate of change can be defined the same way the slope of a curve or slope of a tangent line is defined, let's take a look at that first. So in the previous video, I defined slope of a curve by taking 2 points and moving the 1 point closer and closer and closer to the other point. It can't equal the other point because then I wouldn't have 2 points to define my slope of the line. So we're approaching it without actually equaling it, means we're finding the limit as the points get closer and closer together, which means the change in x is approaching 0. So we define slope of a curve or slope of a tangent line as the limiting value of delta y over delta x as delta x approaches 0. Then we define that more specifically in terms of those 2 points. So the slope of the curve or the slope of the tangent line is the limiting value of this y value, f of x plus delta x, minus this y value, f of x. So that's the difference or the change in the y values, divided by the change in the x values or delta x, as delta x approaches 0. What we're going to talk about today is the same thing, but it's going to be the instantaneous rate of change of a function. So the definition of instantaneous rate of change of y with respect to x is the same as slope of a curve or slope of a tangent line to a curve, and that is this limiting value as delta x approaches 0. Let's take a look at using this to find the instantaneous rate of change of a function. So in this example, if we had y equals 2x squared minus 1, we could find the instantaneous rate of change of this particular function as an expression, so for any value of x, and then we could find it for specific values of x. Here's our definition. We're going to use this to find an expression for the instantaneous rate of change of this function. And then I'll talk about how you can evaluate it for specific values of x. So in this definition, we need to know what f of x is. That is going to be 2x squared minus 1. So that goes in for f of x. I also need to know what f of x plus delta x is going to be. I talked about how you do this in a video on functions, but basically you put this expression in wherever there's an x. So instead of x, we write x plus delta x. Now I'm going to expand this before I plug it in, and just to make it a little bit easier. First of all, I'm going to square this, so I'm going to take x plus delta x times x plus delta x. Be careful, don't square each term. That is not proper algebra. So when I do multiply properly, I will get x squared plus 2x delta x plus delta x squared. Now I'm going to multiply each of those terms by 2, just to get rid of those parentheses. So f of x plus delta x will equal this. I'm going to plug that in to this part. So my instantaneous rate of change will be equal to the limiting value of 2x squared plus 4x delta x plus 2 delta x squared minus 1. That's f of x plus delta x, minus f of x, which is 2x squared minus 1, all over delta x as delta x approaches 0. In order to find this limit, I have to simplify. I can't put a 0 in for delta x because that would make our denominator equal to 0, and that's undefined. So I'm going to start by combining like terms. So 2x squared minus 2x squared is 0. Negative 1 minus negative 1 is 0. So I'm going to be left with 4x delta x plus 2 delta x squared over delta x. I'm going to continue simplifying. I could factor 2 delta x out of the numerator, but I'm just going to factor delta x out. And I'll be left with 4x plus 2 delta x. Now that I have delta x factored out, I can cancel that factor with the one in the denominator. And I'm left with the limiting value of 4x plus 2 delta x as delta x approaches 0. I now can put 0 in for delta x. And when I do so, I'm actually finding the limit, so I don't write limit again. So it will be equal to 4x plus 2 times 0, which is just 4x. So 4x is the expression for the instantaneous rate of change of this function. So if I wanted to evaluate it at a point on this graph, I would just plug my x value in to determine that. So for example, if I said, what's the instantaneous rate of change when x is equal to 5? We would say the instantaneous rate of change would be 4 times 5, which would be 20. If I said, what's the instantaneous rate of change at negative 3? Again, I would just put my x value in and I would get an instantaneous rate of change of 4 times negative 3, which is negative 12. So negative 12 slope there and 20 slope when x was 5. So now we can evaluate it for any values. This is the long way of finding the instantaneous rate of change of a function. We're using our limit definition, and fortunately you're not always going to have to do that. You will probably be expected to do it this way initially when you're learning calculus because they want you to have that understanding, but luckily it gets much easier. My next video is going to be on derivatives, and I'm going to do derivatives the same way. And then after that video, we get into finding the easier way of finding slope of a curve, instantaneous rate of change of a function, and derivatives. So you probably will be expected to do this for a little while initially, and then it gets much easier. So hang in there. Don't get too intimidated by this. Go back and review functions if you're getting lost here, but we're using the same definition for all three concepts. All right, take care, and we'll see you on the next video.